Hello everyone, today we are going to discuss a new model of writing backend applications which reduced latency up to 15x and decreased cost by 9x for Google in a prototype. The video might be a little long today, but stay with me, I'm super excited to talk about this. Okay, assume this. You have two services, one for showing up a dashboard and other for fetching user data. Let's call them the dashboard service and the user service. When you think about microservices, how do you think them working together? You would have two separate containers entirely, and they would talk among them using some generic communication protocol like HTTP with JSON or gRPC, something like that. When you make some changes in one service, this might have cascading effect on the other service as well, and you will figure out a way to deploy them both together somehow, and you will manage it. You can scale these services independently of each other. They are also fault tolerant, like if one service goes down, it does not take the other one down with it, right? So it's pretty great stuff. But like with everything in software engineering, with great stuff, there is also some bad stuff too. And we will talk about that in some time. For now, notice something. In here, how you write your code is strongly coupled with how your code is deployed. The physical boundaries of your code, which is how your code is running, has to follow the logical boundaries of your code, which is how you have written your code. This is always true in microservices. This is the fundamental observation, and the fundamental question is, why does this have to be true for any distributed applications currently with the microservices architecture? Why can't we write modular code, each module handling a different part? But that is not how the code is deployed, which means both the dashboard service and the user service can run in the same container, or maybe even in the same process, or maybe in different containers entirely. We really don't care. Now, this is the problem which a paper called Towards Modern Development of Cloud Applications is trying to solve using a modular monolith architecture. It is published by Google, and today we will discuss the ideas and architecture proposed by this paper. You can see that the first author in this paper is Sanjay Ghemawat, a titan of our industry who, along with Jeff Dean, brought numerous game-changing software to our industry like TensorFlow, like MapReduce, and so on. So when he says something, you better take it seriously. Before talking about the challenges, it's important to talk about the benefits of the current microservices architecture, because we need to keep these benefits in our new model as well. Well, you can see you can scale each services independently. That's the first benefit. If one service goes down, the other isn't affected, so it's fault tolerant. It requires clear, explicit API definitions between the components, so that encourages better development practices, and it allows for flexible rollouts. So one service can have different release schedule, another service can have different release schedules, so teams can have their own release schedules and not conflict with each other. Now to the challenge of microservices. The paper mentions 5 challenges numbered as C1 to C5. Challenge 1, it hurts performance. You may draw 2 boxes during your system design interview and a line between them, but that line between them is a network connection with real latency. It has to send data across the line, which needs to be first deserialized into something like JSON, then deserialized from JSON later. All this is not cheap, and it is easy to get carried away when writing systems like this. Challenge 2, correctness. It's pretty hard to test multiple microservices and interactions between them. It's often challenging to prevent one version of the microservice talking to a different version of another microservice, and they're not compatible and they break. The paper mentions a case study of over 100 catastrophic failures, and 2/3, get it, 2/3 were caused by interactions between multiple versions of the microservices. This is not something inherently wrong with the architecture itself. It's just a pit which is pretty easy to fall into. Challenge 3 is that it's hard to manage. There are multiple binaries to build and deploy, to test for correctness, security, and it is also difficult to build all of them and test locally. The fourth challenge, C4, is that it freezes APIs, which is kind of good, but it also has its disadvantages. It becomes hard to change one API in some component without breaking some other dependent microservices, which you might not really know a lot about. Lastly, it slows down application development. Due to all the things mentioned above, if you change multiple microservices, you need to plan to deploy all of these microservices carefully, which might have their own release schedules. There is no set rule on how to deploy the changes in multiple services, so you need to think through it. All this planning slows down your application development. To tackle these challenges, the authors propose a programming methodology with 3 core tenets. Write monolithic applications separated into clearly defined logically distinct components, which means a modular monolith application. Use a smart runtime to map these logical components to physical processes. So you see, the responsibility on where to run or deploy a particular service is not on the programmer. It's on something called a runtime. You can write your code without worrying about where and how it will run. The last tenet is that deployments must happen atomically, which means a version deploy should either succeed for all the services or none of them. Even if you change multiple components, you should not sit around and plan how to deploy it. The framework would take care of it, and different versions of the components would not be interacting with each other. So all the services and the components would be taken to the next version, or nothing would be. With these tenets in mind, they propose a solution with two paths. One is a programming model, the other is a runtime. The programming model basically is how you structure and write your code. The runtime takes care of how and where your code will be run and how and where your code will be deployed. Before diving in deeper, let me give you a little bit of summary on why this seems like a good idea. Look, the runtime has full visibility on how the services would interact with each other and can deploy them optimally. Think about this. When the runtime knows that two services talk to each other a lot, they can place them closer to each other, maybe on the same process or the same host, so they can communicate with lower latency. So the runtime is essentially co-locating these services instead of keeping them in separate containers. This transparency to the runtime speeds things up. I will also discuss this point in more detail from the perspective of serialization and deserialization and how that brought massive performance gains. You see, what the runtime is doing is taking the worries of deployment planning from the developer. The developer can write their code in any way. The runtime for the modular monolith would take care of the rest, like magic. Alright, you got the summary now. Let's dive deeper into the programming model first. We will come back to the runtime later. The programming model revolves around the concept called components. You can think each component is each of your service. In the case of modular monoliths, component stands for logical separation first and foremost. How they will be deployed is not our concern. So two components may run on separate processes in separate machines or on separate machines altogether. Things that apply for a microservice works for components too. They can be replicated, they can be scaled up or down independently, they can fail and get restarted, all these things. To move forward, look at this Go code from the paper. This is how we are defining an API for a component, or declaring a component basically using an interface. The API is basically the function signatures. Any other component which want to interact with this component has to call this function to talk to it. Now the API is defined by this interface for the component, and it has to be concretely implemented using this struct, which embeds this implements hello to signify that it is inheriting from the hello interface. The init function initializes the component, and this is where we get the object of a component. And you see, we are calling the greet function here. Now this greet function call might be behind the scenes a RPC call, like a network call, or simply a normal function call. We don't really care. We just call the function. What happens in the background, how the services communicate with each other, is taken care by the runtime, not by us. By the way, all this code is written using a library called Service Weaver that Google released along with its paper, with which you can write modular monolithic applications. I will not cover the library today in detail, just the ideas. Okay, let's talk about the runtime now. As I said earlier, the runtime takes care of where the components are run and deployed. It takes care of the low-level details for this. Now, there are some more responsibilities that the runtime needs to take care of, and the first one is called code generation. Look at this code again. You see that we are making a function call here. Now this can be a inter-process communication call or remote network call or just normal function call, anything. Thus the runtime generates the required code for communication and builds it along with the application code in a single binary. It generates more code to deserialize and serialize the arguments sent through these things. So it basically takes care of all the invisible magic that is required for communication between these two components. Now, this is not the only place it generates code. There are some more places it generates code as well, but code generation is the responsibility of the runtime. Another thing that it takes care of is atomic rollouts. The paper speaks against rolling updates, where each service is updated one by one, and in the meantime, service of one version can talk to the service of another version. And this can lead to many unintended errors. they wanna follow something like blue-green deployments, where they would deploy all the services of the next version and then gradually move the traffic from the older version to the newer version. Now that you know what the runtime does, let's talk now about how the application talks to the runtime. Now the video might be getting a little bit longer here. Stay with me, there's a lot to learn here. There is this little thing called a proclet, which sits between the application and the runtime. It runs as a daemon and connects to the API that the runtime provides. It becomes sort of a mediator between the application and the runtime. So it's like a gateway. Now the runtime exposes APIs to the proclet like register replica to register the proclet, start component to start executing a component, and some others as well. You can read the full list in the paper, or I've just pasted a screenshot here. Look at this diagram from the paper. The runtime is expected to be something like this. It should act like a control plane, and as I said, manage stuff like determining where to run the components. It should also manage the rollouts and all these sort of things. It's sort of like Kubernetes for modular monoliths. I mean, not a perfect analogy, but we can start with something like this. It should also have envelope processes, which would help the global manager to connect to these proclets using Unix pipes. Now the runtime should also be aware of the environment it is deployed in and act accordingly. So whether it is running on AWS and GCP or Azure, it should act accordingly, and there should be no difference to us, the programmers. It might also do stuff like logging, metrics, and other things to make your life a little bit easier. So this was the overall design of the runtime. Let's see one of the very interesting things that this design brings us. It is sort of an example of a scenario where this kind of an architecture can benefit us a lot and bring us a lot of value. Now in the traditional microservices world, services would talk to each other using something like JSON. Let's say they are exchanging this person data with name and age. It would be first serialized into the JSON text format. The JSON would be sent here, and then it would be deserialized again to get back the object. This serialization and deserialization is kind of time consuming. So let's try to get rid of this. As I said, due to atomic rollouts, all the components are of the same version. It has to be. Two components will always know exactly the data they are transferring between each other. Both of them are guaranteed to have the same model. Now, since component B in this case knows exactly the data format and the data structure that is going to come from A, if the format on A changes, that would mean a completely new version for both A and B, and both A and B have to be redeployed again. Since we have this guarantee, we don't actually need a generic data format to exchange data. We don't actually need JSON. We can dynamically create a custom data format where each service node, what fields are to be read, where to read it from, what are the lengths of each field, what is the order of the fields that is saved. So we can just send these encoded data, maybe just a normal byte array across the network, and service B knows already what to read, from where to read, to get back its person data structure. So it does not really need to go through all the JSON serialization. And this was the main reason behind the performance boost that the authors got in their benchmarking, where they found like 2x improvement. And this benchmark where they found 2x improvements was done on each component running on separate instances. So it's not really using the full power of modular monoliths. And when they co-located all the components onto a single OS process on a single instance, they found 15x, get that guys, 15x performance improvement, which is tremendously good. And they also reduced their costs by 9x, all while maintaining the same requests per second rate. Now, we should always take benchmarks with a pinch of salt, since all use cases differ. You might not see the same kind of improvement in your use case. Nevertheless, it says the approach is at least promising. Now, does this mean that microservices are dead? In my personal opinion, I do not think they are going away completely very soon. But it's clear that there is some kind of trend to consolidate microservices into some kind of monoliths for simplicity, performance, and most importantly, cost savings. There are also many other things to consider, non-technical things, like how easy will it be to migrate your old code to this new structure. There might be issue. Another issue might be that what to do with multiple teams owning separate services. If they work on the same modular monolith, there might be a lot of back and forth between them in maintaining the same modular monolith, and that might slow them down. Well, for the last point, the Service Weaver website actually mentions that each team can own their own modular monolith for all the services they own and deploy it on their own way, and two modular monoliths owned by two different teams can talk to each other like normal microservices does. Now, does this defeat the entire purpose of having this? Well, frankly, I don't know, and I can't say until I've seen a large project on this and worked on it and seen relevant benchmarks for it. Do put down in the comments what do you think about this kind of an architecture. Would love to see the discussions. Although, like most technologies, only market and time will give the final verdict, not you or me. Thanks for watching. Leave a like and subscribe to this channel for more interesting engineering coverage. This is Ankush signing off.